terms. You're probably wondering about all of them. This is what I will talk about. I will link the in-situ dating with its application in mineral exploration. So let's start with the basic. What is geochronology? Geochronology is the science of measuring the age of Earth materials like minerals and rocks. In geology, understanding the mineralization periods linked to global tectonic processes is important to identify prospective mineral deposits. With the right technology, we can trace ancient tectonic events and determine when a rock or mineral deposits may have formed. We can link the rock forming process to these events using geochronology and geochemistry. And we can link this events to using the geochemistry and geochronology to understand the distribution of these events or of these ore deposits around the world. So how can you use geochronology to measure the age of Earth materials? The short answer is using radioactive isotope. Now you may wonder, what are isotopes? They are atoms with the same number of neutrons, of protons, but different number of neutrons or mass number. Some of these atoms are radioactive and unstable, so they decay over time in a predictable way to reach stability. They decay alpha or beta or gamma. In alpha decay, as we see here in this slide, the radioactive atom, or what we prefer to call the parent atom, produces alpha, and this reduces the atomic number by 2 and the mass number by 4. For example, here, uranium-238 decays alpha and changes to thorium-234. In beta decay, the parent atom emits a beta particle. The beta particle has a negative charge, and this increases the atomic number by 1 without changing the mass number. This type of decay results what we call isobar, where the parent and daughter atoms have the same mass but different atomic number. Rubidium, strontium, and a good example for this kind of decay. Cobalt-60 is an example for gamma decay. It undergoes beta decay first, converting a neutron into a proton and forming nickel-60 in excited state. This nickel-60 releases this excess energy as in a gamma form to reach its stability. Now, how can we use these isotopes for age dating? Radioactive decay happens at constant rate known as decay constant. The time it takes for half of radioactive substance to decay into its stable form is called half-life. Some isotopes like uranium-238 have long half-lives, around 4.5 billion years, making them ideal to dating oldest rock in Earth. Others, like carbon-14, have much shorter half-life, just 6,000 years, and are used to date more recent materials such as bones. It's like have different tools in a toolbox. Each isotope system can be used for a specific purpose, depending on the time scale we are investigating and the temperature, the closure temperature of each system. Let's have a look at some of these isotopes. With uranium isotopes with half-life of 4.5 billion years for uranium-238 and 700 million years for uranium-235, we can date ancient igneous and metamorphic rocks, and we can also date mineral deposits associated with granitoids, and we can also constrain the timing of deposition of clastic rocks. For potassium-argon and argon-argon system, they are widely used for dating volcanic rocks, and we can use them to understand the thermal history of ore deposits. Rubidium-strontium system is frequently applied to date metamorphic events, hydrothermal process, and the low-temperature alteration process. Samarium neodymium can be used for understanding the mantle process. Rhenium-osmium system can be used to date sulfides minerals, especially those containing molybdenum, nickel, and copper. Lutetium-hafnium are suitable for dating garnet in metamorphic and hydrothermal systems. This is the complicated thing. To determine the age of the rock or mineral, we need to analyze them for their isotopic composition. And we can use this composition in these equations to calculate the age. I will skip this complicated math. Just remember this. To get the age of the sample, we need to analyze their isotopic composition. So we need precise measurements of these isotopes, and we can do that using the mass spectrometer, or what we call mass spec. The mass spectrometer works by identifying or measuring atoms or isotopes based on their mass. On this slide, the first one here, we can see the inductively coupled plasma mass spectrometer, the triple quad one, at the University of Adelaide in Australia. The second one is the noble gas mass spectrometer in Australian National University, and the last one is the thermal ionization mass spectrometer at the King Abdulaziz University. The ICBMS shows here is the advanced version of the single quadruple inductively coupled plasma mass spectrometer, and this is cutting-edge instrument equipped with a reaction cell. We will talk about this one shortly. Probably in the industry, the most popular one is the ICBMS, the single quadruple ICBMS, because it's used commonly for geochemical analysis for major and trace elements, and also for in-situ uranium lead dating. Remember this, the mass spec relies on the atomic mass number to distinguish between isotopes. So if we have two isotopes with the same number, the mass spec cannot distinguish between them. This issue is known as isobaric interference. When we are working with beta decay system like rubidium, strontium, rhenium, osmium, lutetium, hafnium, we will face this issue. For this reason, the ICBMS is not ideal choice to analyze these isotopes. And we need to separate between these isotopes in chemical lab to avoid this overlap, which is time consuming. And after that, we can load the sample or analyze them using the thermal ionization mass spectrometer or the multi-collector ICBMS. Now let's talk more about beta decay system. These systems are characterized by their long half-lives, and they are useful for determining the age of ore deposits, the timing of events that form them. As I said, the challenge of these isotopes, both parent and daughter isotopes have the same mass number, and the mass spec cannot distinguish between them. Until recently, most of these systems were inaccessible for routine in-situ analysis. You may ask now, why do I need in-situ analysis? The advantage of the in-situ analysis is that it can be performed rapidly at low cost with minimal requirements for sample preparation. Sample can be introduced to the machine in solid state rather than the liquid state, and also we can constrain the age zonation within the single grain. We can understand the textural relationship between the mineral phases, and we can also target larger grains with minimal risk from isotope disturbances, and we can avoid inclusions, and other source of contamination can exist in the sample. So considering the benefits of the beta decay system to constrain the age mineral deposits and the timing of events that shape them, it will be great if we can analyze the samples using in-situ method. The answer for that, or the solution for that, is the triple quadruple inductively coupled plasma mass spectrometer. This advanced version of the single quadruple inductively coupled plasma mass spectrometer, ICBMS I would say from now, is equipped with a reaction cell placed between two quadruple. This is the first quadruple, this is the second quadruple, and the reaction gas is placed between them. What is the function of this reaction gas? We can fill this reaction gas with different kind of gas, and we can perform the chemical separation of beta systems isotopes online within the machine with no need for chemical lab. To do that, we need to link the machine into a laser ablation system. And the laser ablation system can be used to target the phase of interest with a laser beam, and the diameter of that laser beam can go down until 70 micron for rubidium strontium method, and until 30 micrometer for uranium lead method. The laser beam will hit the sample surface and generate aerosol, which will be carried out into the instrument. And in the instrument, the aerosol will pass the first quadruple, and we can set the first quadruple to eliminate certain masses like 103 or 102, and allow the rest of them to go inside the instrument. When for example, here we have rubidium and strontium passing through the first quadruple. In the second phase, which is the reaction cell, strontium will react with the nitrox oxide, which we fill it in the reaction cell, while the rubidium will not react. So we can detect rubidium on mass and strontium on mass shifted as strontium oxide, and the mass of strontium oxide is 103. For this reason, we exclude 103 mass from the beginning, so it wouldn't interfere at the end of the system before the detector. We can apply the same principle to other systems, other beta systems. For example, lutetium hafnium can be separated in the machine using ammonia. Rhenium osmium can be separated using methane. And potassium calcium can be separated using SF6. And we need to mix it with helium and hydrogen to avoid the interference with argon, which is the source of the plasma in the instrument. Now let's take you to a real case study to see how we can use in-situ dating, in-situ rubidium strontium dating, to determine the age of the key events that shape Jabal al-Abla. So Jabal al-Abla is a known ancient gold mine site located in the southeastern part of the Arabian Shield, and specifically in Shwas Belt. And the Shwas Belt is intruded by a diuretic unit, and the entire region has been affected by a major structure called Farwa Shear Zone. The diuretic complex showed here, it's called Abla Shwas Plot, and it's intruded by several granitoids shown here in red, and Abla pegmatite is shown here in blue. Closer look at Jabal Abla. It's composed mainly of pegmatite, and this pegmatite is composed of feldspar, muscovite, and quartz. The mineralization is associated with the alteration zone within the pegmatite, and these alteration zones are closely linked to the quartz veins. In the left side in the photo, on the left side, we can see the horizon zone at the top of the pegmatite and the quartz veins. We collected sample from this exposure for rubidium strontium dating for two reasons. We wanted to constrain the timing of the crystallization of the pegmatite and the timing of the alteration event. The analysis were conducted using the Agilent 8900 ICP-MS at the University of Adelaide, linked to this laser system. Here you can see the sample holder of the sample systems. At the top is our samples prepared as thin polished section. And this is the advantage of the in-situ dating. We can analyze the samples directly in solid state with no need to dissolve them as a traditional way. At the bottom here, we can see the standards or the reference materials we used for calibration and quality control. We investigated these sections under the microscope, and we noticed that there is two distinct phases of muscovite. The primary muscovite is shown here in figures A and B. The secondary muscovite is shown here in figures C and D. For the primary muscovite, it found in pegmatite and the horizon away from the alteration zone. These crystals are typically large, eohedral to subhedral, while in the secondary muscovite were found in the alteration zone appeared as the small subhedral to anhedral crystals. We also generated chemical maps for these muscovites using the scanning electron microscope equipped with the XRF to investigate the chemical differences between these phases. The elemental map showed that here at the bottom, the primary muscovite has higher iron content compared to the secondary muscovite. Here is the result of the age dating. We dated the two phases, and the primary muscovite yielded age ranged between 336 and 636 and 611 million years. The secondary muscovite yielded younger age ranged between 608 and 598. To get it clearer, I calculated the single age for each analysis from the previous isochrons and plot them here in this box plot. As we can see at the bottom here, this group is representing the primary muscovite, and it's older than the secondary muscovite presenting in the above group. From this case study, we can see how in-situ dating is a powerful tool for determining the age of at the microscale. So from that slide, we saw that the primary muscovite likely preserved the crystallization time of the pegmatite. Meanwhile, the secondary muscovite preserved the timing of the alteration. So this is one of the advantages of the in-situ dating. We have measured these ages at microscale, and this allows us to determine the age of mineral deposits and the geological events that shape them using diverse set of isotopic systems. Unfortunately, despite its potential, there is currently no geochronological lab in the region can offer this advanced dating method. Here at King Abdulaziz University, we are happy to collaborate with any organization keen to establish a geochronological lab with this technology here in Saudi Arabia. I will leave my contact at the end of this slide, so just drop me a message and I will take it from that point. Regarding the limitation in-situ dating beta system, for beta system is still limited to certain type of minerals because of the lack of standards or reference materials. These standards are required to calibrate the results and for quality control. Developing these standards is still an active area for research, and using this research will help us to expand the technique and to be applied to different mineral systems. It's worth to mention that the ICP missile presented here, the triple quadruple, is an old version, and now in the market there is another version equipped with multi-collector which can provide us with better precision. This brings me to the end of my presentation. Thank you very much, and I'm happy to take your questions now. Okay, no questions? Yes, go ahead.
Hello, I have one question. You said it is compulsory to make the age analysis before isotope analysis, as I understood. It's true?
It's important to calculate the age. We need isotopic composition of the sample to get their ages.
Yeah, but I understood. Okay.
Okay.
Thank you very much.
Go ahead.
Great. I just wanted to mention at KFUPM we have a laser ablation high resolution ICP-MS where we can do
Single quadruple or triple
single
quadruple?
quad.
Yeah, this one is commonly used like for
so
uranium lead
uranium
zircon,
lead.
but we cannot use it for beta decay systems.
Yeah, sure.
Yes.
It's true.
And happy to hear that you have it in KFUPM.
Yeah. Thank you.
All right, thank you very much. And feel free to contact me if you have any other questions. Thank you.